If I integrate this, I will have x cubed plus 3. X cubed divided by 3 rather. Then if I differentiate this, u is ln x. So if I differentiate du, I will have, if I differentiate as in du dx, I differentiate du with respect to x, then I will have, remember that identity, one of the identities that was given in the previous class is if you differentiate ln u, we are going to have 1 over u. So if I differentiate ln x, I will have 1 over x. If I differentiate ln x, I will have 1 over x. So automatically, now we will now write our model again, which is integral of u dv, which is equals to uv minus integral of v du. Now u, where is my u? Where is my u? My u is ln x. dv, where is my dv? My dv is x squared. So I have integral of, I can write x squared ln x, which is equals to, what is my u? My u is ln x. What's my v? My v is x cubed over 3. Put in a bracket, minus integral, this integral, v. Where is my v? My v is x cubed over 3. Where is my du? Du can be calculated here and just cross multiply this two. So it implies that du will then be 1 over x dx. So by making du the solid formula here, so I will have du to be 1 over x dx. So du here I will have multiplied by 1 over x dx. Then to solve this, to simplify this, I will have integral of x squared ln x equals to, I'll have x cubed over 3 ln x minus, this x can cancel 1x here, then we'll have integral of x squared over 3 dx. Now I can simplify this further by saying x cubed over 3 ln x. This 1 over 3 can come out, then I have minus 1 over 3 integral of x squared dx. Then here I will have x cubed over 3 ln x minus, this one will now be, if I integrate this again, if I want to integrate this again, I'll have x cubed over 3. So then I can add plus c because it's definite. Then here now we have x cubed over 3 ln x minus 3 times this, that will be 1 over 9 x cubed plus c. Now you can see that this and this, one over 3, okay, x cubed over 3 is common, so I will have ln x, and this one minus 1 over 3 plus c. So this will be the answer to the integration by part of this. Because when you see this, why they call it integration by, how are you going to know whether it is integration by part? When you have a situation where a particular term or a particular parameter continue to reoccur in the system, you know that they are multiplying each other and they continue to appear in the system. When you integrate this now, you can have a true value. So you know that, okay, definitely this one is integration by part. So I will talk about the B. So this is the B part. We see also resolve to this one. You can differentiate this easily. While this, you can integrate this easily. So this one can be dv and this one is u. So you must not choose your dv and u. The one you can differentiate easily, that you have a true constant or you have a true value or you have a true term, then that is the one. So I know that, me looking at this, I know that ex, if I differentiate it, I will have exponential x back. Then this one, I can integrate this one easily because my interest is to look for dv. I cannot integrate this directly. So that is why dv with x squared will be my dv, u will be my exponential x. So when I write the formula, integral of u dv will definitely be u v minus integral of v du. Then here I will have u. What's my u? My u is ex. So let me differentiate du. I want to differentiate u with respect to x. I will still have this back. Then I can make du, this other formula, then it becomes e exponential x dx. Then the other part, you have dv to be equals to x squared. If I integrate this, then this one will give me v, and this one will be s cubed over 3. So I go back to my formula, which is integral of u. What's dv? dv is x squared. What's u? Your u is exponential x. Then it will be equals to u. What's my u? My u is exponential x times v. What's my v? X cubed over 3 minus integral of v. What's my v? S cubed over 3. X over 3. What's du? du is x exponential x dx. That's my u. Exponential x dx. So you have exponential x dx. Then here you have integral of x squared exponential x, and this one will give us s cubed exponential x over 3 minus this one can come out of this, then I have 1 over 3 integral of s cubed by x dx. So as you continue to integrate this, you will discover that this will continue to repeat. So we can stop this and plus c. We can still integrate this further, but that is because of the fact that exponential x does not terminate easily. So when you come to integrate, it will be increasing. It will be increasing. So we, at the end, we just connote this with a particular identity. Let's say I, to show that it terminates at that point. But in the real sense of it, this exponential x does not terminate. So we can just resolve it. Then I'll say let a to be integral of x cubed e exponential x dx. So then I'll just write x cubed exponential x over 3 minus 1 over 3a, where a is the integral of that. Integration by partial fraction. If you are to integrate using the concept of partial fraction, it is very important that we must be conversant with partial fraction. And when we talk about partial fraction, you'll be given a particular fraction, let's say this for example, and they asked to split it. Can be asked to split it. So definitely you factorize this, which is x squared minus x minus 6, which we did previously. You have x squared minus 3x plus 2x. I want to factorize this, and I have this. Then I have x into x minus 3 plus 2 into x minus 3. And this one will be x minus 3, x plus 2. So automatically that means I can break this to a over, when I split this, definitely I will have x plus 1 over x squared minus x minus 6, which is x plus 1 over x minus 3, x plus 2. So I can split this to x minus 3 plus b x plus 2, and this is what is known as partial fraction. We need this concept in this subtopic, that is integration by partial fraction. So let's see some example. We have to solve this, or we have to simplify or resolve or evaluate. Can come in diverse ways. Evaluate. We have to evaluate this. Then we have integral of x plus 1 over x squared minus 3x plus 2 dx. The first thing we have to do is to move this out, which is x squared minus 3x plus 2. So we simplify this by factorizing it. Then we have x squared minus 2x minus x plus 2. And this one will give us x is common, x minus 2, minus 1 is common, x minus 2. Then we'll have x minus 2, then we'll have x minus 1. That means we can rewrite this, then we have x plus 1 into x minus 2, x minus 1 dx. So what is meant by partial fraction now is to resolve this to partial fraction. Then we'll have x plus 1, so x minus 2 into what? X minus 1. Then let's say, since you have a constant on a linear, the first linear, this, then also have another constant on another linear, x minus 1. That's partial fraction, where a and b are constants that are unknown. So the first thing we have to do is look for the SCM. The SCM will definitely be x minus 2, x minus 1. So we multiply both sides by the SCM. So if you multiply this by this, we are going to be left with x plus 1, which is equal to, if you multiply this by this, we have a x minus 1. If you multiply this by this, we have plus b x minus 2. That's what we're going to have. Then we select critical points, because in partial fraction, what we have to do is we are looking for two constants. But the two constants cannot both be determined. You can't determine them at the same time. So that means we have to determine one first, then we can now determine the other. But for this case, we can see that if I want to eliminate a first, then I will pick a particular critical value for x that will eliminate that a. And that method is what is known as cover-up rule. So cover-up rule is telling me that I can say let my x be 1. If my x is 1, 1 plus 1 on this side is equal to a into minus 1. A is, I say let x be 1. So I'll have 1 minus 1 plus b, which will now be 1 minus 2. 1 minus 1 is 0, so this one can cancel a, and that's my interest. So I can calculate my b easily. So we have 2 equals to 0, then this one is 1 minus 2, that's minus 1. Minus 1 times plus b minus b. So which implies that my b will definitely be minus 1. So I've calculated my b for the first case. So to calculate my a, I still go back to my original equation, which is a x minus 1 plus b x minus 2. I still want to apply cover-up rule, but this time I want to eliminate b. If I want to eliminate b here, I will just say let my x